So you're all welcome to today's SPRE seminar. My name is Shay Balagun, and I'm assisting Professor Sinan Kitin with chairing this meeting. The focus of the SPRE seminar, as you know, this quarter is on soft materials and their inherent mechanics. And so in a few minutes, I'll welcome our speaker for today, Jiaxin and Chen, to talk to us about her projects and as it relates to soft materials. And so please post your questions and comments if you have any in the group chat, and I'll announce them at the end of the lecture. Or you're welcome to unmute your microphone and ask those questions at the end of Jiaxin's lecture. Okay, so now I'm going to introduce Jiaxin. She's a fourth-year PhD candidate in the Civil and Environmental Engineering department. She's also a researcher in the Sustainability and Nanomechanics group under the supervision of Professor Angie Akono. For her academic background, she has an undergraduate degree from the Harbin Institute of Technology in China, a master's degree in structural engineering from the University of Illinois at Urbana-Champaign. She's also a graduate student and a postdoc advisory board member in the Center for Integration of Research, Teaching, and Learning at Northwestern University. I'd like to know more about that center. And also she has broad interest in research in additive manufacturing, materials characterization of geopolymers, nanocomposites, and a host of other materials. So it's with great pleasure that I introduce Jiaxin Chen today, and please go ahead and share your screen.
So first of all, I want to thank Professor Balagun's kind introduction for me, and this is my own. Let me see. Can you guys see my screen? Okay, cool. And I want to thank Professor Balagun again for the kind introduction, and it is my honor to represent our group, and present this collaborated research here at SPRE seminar. And my name is Jiaxin Chen again. You can call me Jiaxin or you can call me Chen. And today I'm going to tell our science story about the fracture properties of the alkali-silica gel using microscopic scratch testing. So first of all, I want to acknowledge the contributions by my colleague, Caroline V. Johnson, and me, and Dr. Nico Hasparak from Brazil, and Professor Paula Montero from University of California, Berkeley, and my PhD advisor, Angie Akono at Northwestern University. And also this work has been published in the Cement and Concrete Composites using the same title and the same contributors named Fracture Properties of the Alkali-Silica Gel using Microscopic Scratch Testing. And this was the foundation starting work of my research career back in 2016 at UIUC. I will first start from engineering problem and research approach, including theoretical development of fracture model and our experimental method. In addition, our results and our conclusions. This is a picture of the ASR cracking. So first of all, there are three keywords in this title, definitely. The first one is the fracture properties, and the second, alkali-silica reaction gel, and the third, microscopic scratch testing. I will introduce the main word, alkali-silica reaction gel first, and explain why we want to know the story behind it. I know there are definitely a lot of experts in our department and also at the SPRE seminar right now, working on alkali-silica reaction and fracture mechanics and also cementitious materials. I will just give a brief introduction of alkali-silica reaction. First, I show some concrete with cracks, and I will talk about the alkali-aggregate reaction first. So alkali-aggregate reaction called AAR was discovered over like 60 years ago in 1940s. People observed cracks in many infrastructures. Some aggregates react with the alkali hydroxides in concrete and causing expansions and cracking over a period of many years. A government report, which is the last image, by DOT showed that it occurs many places from East Coast to Western Coast across America. Definitely, this is not a full map of America. There are two forms of alkali-aggregate reaction, including alkali-silica reaction, which is our topic, and alkali-carbonate reaction. I will first talk about alkali-carbonate reaction. It is observed with certain dolomitic rocks. Alkali-carbonate reaction is relatively rare because aggregates who may have this problem are usually unsuitable for use in concrete for many other reasons. Therefore, we mainly focus on our topic, the popular cracking reaction, alkali-silica reaction. There are three elements to cause alkali-silica reaction. The first one is the reactive aggregate, which may contain certain forms of silica. The second one is high pH, which may come from alkali hydroxide in concrete. The last one is water. Here's a picture I got from a YouTube video on the right-hand side. The left-hand side concrete is inside the building without any water exposure, while the right-hand side is outside the building, and sometimes definitely it rains. It is just a $1 away. We can definitely observe cracking for the one with water exposure on the right-hand side. This is why alkali-silica reaction usually occurs around dams. And silica will react with alkali hydroxide in concrete to form a gel that swells and it gets water from the surrounding cement paste or the environment. These gels can produce enough expansion pressure to damage concrete and to cause cracks. We definitely don't want cracks. So let's take a closer look at the alkali-silica reaction. When I look at the cracks, it reminds me of the Evanston map I got from Google Maps. By the way, I got the idea from Professor Taylor Lay. When we look at the roads on the map, we can see them as cracks. Alkali-silica reaction is also called MAC cracking as well. Let's see where the alkali-silica reaction gel comes in place. Here's an illustration from 2019 Figaro et al. This reaction occurring between the amorphous or polycrystallized silica contained in some types of aggregates and the alkali from the cement paste produces a gel. That is alkali-silica reaction gel. In the presence of water, and alkali-silica reaction gel expands and produces a pressure on the solid skeleton, causing overall swelling and microcracks formation in the concrete. Alkali-silica reaction gel causes cracks on the surface, but when the cracks get bigger and bigger, water and chemicals immerse inside the crack and will cause bigger problems. The long-term behavior of concrete structures may depend on various chemo-physical damage phenomena. Among them, the degradation induced by the alkali-silica reaction is of particular concern for the safety assessment of several concrete dams and bridges, particularly for those that built decades ago. Many researchers have found that alkali-silica reaction gel expands, decrease the compressive strength of the concrete, decrease the tensile strength, modulus of elasticity, and decrease fatigue performance, and even shear strength. So what did we do to have a better understanding of the alkali-silica reaction gel? from atomic scale, definitely we have experts in this atomic scale in our department. ASR structure to microscale level, which is where our research fitting our ASR gel, and then to the centimeter level of ASR damaged concrete. At higher levels, such as macro scale levels, we have mathematical models to predict ASR damage and simulation models developed at our department and Northwestern University CEE. We mainly focus on problem at millimeter level in our group. Hopefully, we can provide some understanding of our ASR gel. In addition, the fracture behavior of AS gel is so important to fully describe concrete deterioration and cracking due to the ASR reaction. So here is a picture of furnace dam in Brazil. And our samples were actually collected from the furnace dam in Brazil by Dr. Nicole Hasparak and Professor Paula Montero. I will give a quick introduction of this dam and its history related to ASR. The occurrence of the alkali-aggregate reaction in the concrete of the furnace dam was first noticed in 1976. The areas of greatest concern were the cracks on the top of the spillway columns, in the anchorage blocks of the water conduits, and in the powerhouse. In addition to the unleveling between the central wall and adjacent blocks, in 1996, the first laboratory study was done with concrete cones from columns of spillways, and laboratory results showed that a significant decrease in modulus of elasticity of the concrete columns. After that, in 2002, sadly, with the great incidence of extruding gel in concrete surfaces of dripways, a more comprehensive drilling problem was performed, and the concrete cones were studied in the laboratory through mechanical tests, expansion tests, and microscopic analysis. It is definitely possible to obtain centimeter-sized gels from the inside of the galleries in a dam. But even so, the ASR gel crystals are typically too small, less than 10 millimeter, as shown on the right-hand side. It is really hard and challenging to perform traditional microscopic tests such as uniaxial compression or three-point bending test. Therefore, in order to obtain the fracture behavior, we need to figure out the right solution. For the ASR gel crystals from the same furnace dam, to have an overall idea of these materials, previous studies have shown that material properties have been characterized by Professor Moon and Dr. Nicole, Professor Montero's group previously. X-ray diffraction results showed amorphous properties. In addition, Dr. Tom Bailey used the Fourier transform infrared to identify chemical groups of the ASR gel crystals. Definitely more details can be found in their papers as shown in the reference. But our group focus on the fracture behavior of the alkali-silica reaction gel. How can we characterize this fracture behavior of this small gel? From the image, it has a scale bar of 4 millimeter. For US system, which is around 0.16 in inches. To illustrate how small it is, I got one image online to show 4 millimeter in our hands. You can think of the size of an ASR gel crystal in your hand like that. It is so tiny, so that we can now use the classical method to get its fracture toughness. We used a traditional method, still a classic method, called scratch test, but at micro scale level. The advance of instrumented scratch testing in late 1980s led to a broader range of applications for scratch testing, including but not limited to the strength of ceramics, damage of metals and polymers, polymer films back in 1998, and soda lime glass in 1998, and our current work of scratched cement. Here are some microstructure images of the previous studies using scratch testing. So the basic of the scratch test actually dates back to the Hellenic era, where scratching was utilized to rank minerals according to their relative hardness. Here's a short video by Professor and Abahaka at MIT CS Hub to illustrate the fundamentals of scratch testing. So this is the sample. You can see the flat and smooth surface of the sample. And this is a Rockwell tip. The Rockwell diamond indenter was pushed across the surface of the sample material, while linearly increasing the vertical force as shown on the left-hand side. The penetration depth and the horizontal force were recorded as shown here. Here is the final scratched surfaces. As we can see, the diamond Rockwell stylus was pushing the surface of the materials. The right-hand side is a stylus scratching on our ASR prepared specimen. All tests were conducted using an antimpar micro-scratch tester, as shown here. In particular, the microscope and the scratch testing unit are synchronized so that we can select the location of the test with high accuracy and get an image of the surface after testing. Our tests were carried out using a Rockwell C probe that consists of a hole of half apex angle of 60 degrees, which is the theta here on the right-hand side figure, ending in a sphere of tick radius r equals to 200 micrometer with a sphere cone transition depth of 27 micrometer. The challenge here is to carefully prepare a specimen of ASR gel crystals and design the experimental parameters that can be tested using scratch testing and satisfies the assumptions for obtaining the fracture toughness. For scratch itself, in other words, it is the process when a probe pushing a material surface. They are forming challenge during scratch, the force range, the penetration depth, and the length scale range, and the probe shape limitations, in addition, various deformation patterns. In terms of analytical model of scratch testing, we assume that we would use linear elastic fracture mechanics and aerostrip function for sigma xx, sigma xz, and also phi xz, and the plane conditions were derived accordingly. Consider a scratch test in a linear elastic as chalky material with a crack emanating from the tip of the probe. We can then evaluate the rate of change in potential energy in a material volume surrounding the crack from the perspective of an observer that moves along that crack. This leads to applying the famous J integral to calculate the energy release rate, knowing the stress and strain distributions ahead of the probe. In addition, another important element is the probe shape. When the penetration depth depends on your force on the experimental setup is less than the spherical to cone transition depth 27 micrometer, we are in spherical probe. When the penetration depth is bigger than 27 micrometer, we are in the conical zone. In order to have a simpler probe shape and avoid further decoupling, a careful selection of vertical force needs to be considered. This requirement sets the limit for our experimental force range. To summarize the scratch method, we mainly have 6 steps. First, we start from cutting with the existing crack and then use general J integral L stress function. Afterwards, we start with dimensionless analysis, neglecting rate and thermal effects. Inverse application to get the fracture toughness. Moreover, calibrate with our scratch tape geometry, the probe function. We can then evaluate the rate of change in potential energy in a material volume surrounding the cracked tip from the perspective of an observer. The fourth solution leads to the following equation connecting the horizontal force Ft to the fracture toughness Kc, which is Kc, the last one, equals to horizontal force over square root of 2Pa. And 2Pa is the probe shape function that depends on the geometry of the scratch probe as well as the depth of penetration d. More details can be found in the reference paper. For a spherical probe, the shape function is projected function of the penetration depth. And for a cone probe, it is another function of the penetration depth. Therefore, we calibrate the shape function before testing by carrying out tests on a fused silica reference specimen as shown in this figure. This is a panorama of our scratch test on the fused silica reference specimen to find our probe function. It was found 2Pa equals to 54.51 d over r squared in the spherical region, and where d is the penetration depth and the probe tip radius r equals 200 micron. Talking about fracture, we usually think of fracture energy, GF, by Griffith-Irving formula in linear fracture mechanics. We know fracture energy related to Poisson ratio, fracture toughness, and elastic modulus. We have got fracture toughness using scratch test. How can we obtain elastic modulus of ASR gel crystals? From the image, some of you may think of indentation test, and yes, we did indentation to characterize the indentation hardness and modulus. But what is indentation? To determine indentation, a hard tip whose mechanical properties are known is pressed into a sample whose properties are unknown with the applied load. To better demonstrate indentation, we use Dr. Abhaker and Professor Um's video for indentation demonstration. Here is our sample and the sample holder. When we get the indentation test, the sample holder goes up and the indenter goes down. The Berkovich tape is pressed into the sample surface. And we got the force and penetration depth. And we can also set up a grid indentation automatically as well, as shown here, the first one and the second one. But we have a spacing which is 3 times than the penetration depth to avoid overlapping. Here's the grid indentation result. Let's take a closer look at the indenter and the raw data from the indentation. This is a curve with load and displacement. The left-hand side is the loading part, while the right-hand side is the unloading part. We used a Berkovich diamond indenter on an atom per nano hardness tester. Vertical force P and penetration depth H curves were obtained from the depth sensing equipment. We applied Oliver and Far's method, as shown here, to obtain indentation hardness and indentation modulus. The right-hand side demonstration indicates that the sample preparation needs to be precise and the sample surface needs to be flat and smooth. The same rule applies for scratch testing. We can see it here. So here comes our key challenge of sample preparation. In order to have a uniformly flat and smooth surface with a low roughness, we applied metallographic polishing step. The objective of this step is to increase the accuracy of small-scale mechanical testing. The rule of thumb created by Miller and al. In 2008 is to have a surface roughness less than 1/5 of the maximum penetration depth. Before preparing our sample, to support the sample, we embedded our sample in epoxy resin, whose material properties have been known for the epoxy resin. After that, we used a diamond linear precision saw to cut our ASR gel crystals. We used oil-based cutting fluid to reduce the cutting heat. The reason why we want to use oil-based fluid is because ASR gel crystals is sensitive to water exposures, as I said before. Second, we applied surface polishing using abrasive papers until the grit size is 1 micron to achieve a flat, smooth surface. Microscopic images between steps were used to check the surface roughness and also the surface microstructure. After the final step of polishing, we used a small load scratch testing to check the force profile on the surface. The last image shows our prepared ASR gel crystal specimen ready for scratch testing and indentation test. The number 1 is ASR gel here, and the number 2 is the epoxy resin. We can see a smooth and flat surface for our prepared sample. Previous slide mentions epoxy embedding to contain the shape of ASR gel. I will provide more details here. Each ASR gel specimen was embedded in a 32 mm cylindrical mold filled with epoxy cure resin. Epoxy embedding is used to provide structure support and facilitate the metallographic polishing phase. And the first specimen is air embedded on the left-hand side, which means we embed our specimen in room temperature in the normal condition as shown in the left-hand side. The other, which we call specimen 2, we embedded them under vacuum. In other words, during vacuum embedding, the epoxy resin is pushed into microscopic pools, resulting in a smoother surface. Definitely, we can see it from here on the right-hand side. From both images, it seems like our surfaces look smooth, even though there are some cracks. But because of the pre-cracks from the microscopic images, we know that when we design the parameters of our scratch testing and indentation, we need to have a shorter length and force limitation. Scratch tests were carried out on the epoxy embedded ASR gel crystals. The specimen embedded in air was tested with a maximum vertical force of 13 Newton. For the macroscopic test, this figure of one single scratch testing displays the horizontal force and the recorded penetration depth on the left. The maximum penetration depth is 180 micron. As a result, the scratch probe can be approximated by a cone instead of a sphere. In contrast, we used a maximum vertical force of 10 Newton for the vacuum embedded specimen. During epoxy embedding and the vacuum, the resin is pushed into the microscopic pools due to the vacuum. Unfortunately, this results in a composite structure at microscopic level consisting of the resin and the ASR gel. Therefore, we purposely selected a lower force to obtain a depth of testing in the microscopic range. The maximum penetration depth in this test was 28 micrometer, as shown in the right-hand side figure. The scratch length was 2 mm for both specimens. After scratch testing, the top surface of the specimen were examined using scanning electron microscope at different levels of resolution. Let us take a closer look at the fracture surfaces. The first figure represents the scratch panorama. We can see that scratch starts from the right-hand side and then stops at the left-hand side. The second figure is a closer look at the final location of the scratch testing. When we zoom in, here comes the most interesting part. We observe curved cracks, regularly spaced and perpendicular to the direction of testing. The arrow represents the direction of the testing. At a higher magnification level, new created fracture surfaces can be seen on the right-hand side figure. The presence of these fracture points point towards the predominance of fracture dissipation and motivates of fracture analysis of our test data. The scratch test intrinsically involves a combination of ductile and brittle failure. Therefore, by calculating the geometry, depth to tip radius ratio going to infinity for tests with axial symmetry at symmetrical probes, we achieve a fracture-driven state that enables us to probe the fracture resistance. The quantity, horizontal force by square root of 2pa, converges toward a constant for large D/R ratios, as shown in these two figures, which is evidence of a ductile to brittle transition taking place during the test. Given the homogeneous and amorphous nature of ASR gel, we expect to obtain similar values of fracture properties for both the air-embedded specimen test at a maximum depth of 180 micrometer and the vacuum-embedded specimen test at a depth of 28 micrometer. And our results actually show the fracture toughness Kc is found to be equal to 0.59 plus and minus 0.12 megapascal square root meter for specimen 1, the air-embedded specimen, and equal to 0.62 plus and minus 0.08 megapascal square root of meter for specimen 2, the vacuum embedded, 0.59 and 0.62 is really similar. Both microscopic scratch tests and microscopic scratch tests yield a similar value of fracture toughness Kc around 0.6. Having measured the fracture toughness of alkali-silica gel crystals, we set out to measure the fracture energy, GF, using the Griffith-Irving formula. First of all, we need to get the elastic modulus. There's a relationship between elastic modulus and indentation modulus. There are two microscopic images of the specimen 1 on the left-hand side and specimen 2 on the right-hand side. It is a really small indent. If we take a closer look, we can see the small triangular points on the surfaces. Using Oliver and Fast method, we have our indentation modulus for air embedding of 29.13 plus and minus 7.76 gigapascal and 34.42 plus and minus 2.81 gigapascal for vacuum embedded specimen. In terms of indentation modulus, M represents the indentation modulus. And if we assume the Poincare ratio is 0.32 which is what Professor Moore and al. Did in their paper. Compared to their results, we have a really good agreement. I will introduce more. Moore and al. Carried Brillouin spectroscopy measurements on more than 10 fragments of ASGL crystals, and actually from the same furnace depth as well, and the sample was provided by the same person. And they divided the ASGL in two groups. The major elastic properties of there is 24 plus and minus 2 gigapascal, and with Poisson ratio 0.38 for the first group, and E equals to 27 plus and minus 1 gigapascal with Poisson ratio assumed to be 0.32 for the second group. If we assume the same Poisson ratio of our air-embedded specimen to be equal to 0.32, the measured Young's modulus E is 26.15 plus and minus 6.97, which exactly lies within Professor Moore et al.'s estimate of 27 gigapascal. Therefore, from this perspective, our measurements of Young's modulus agree with other measurements of the ASR gel crystals. After obtaining fracture toughness and elastic modulus using Griffith-Irwin formula, we can obtain the fracture energy. And then for our ASR gel crystals, we have a fracture energy of 11.17 and also 11.95 for the other specimen. And compared with the mortar, which is around 20, and concrete around 60 to 100. In other words, our measurements suggest that the fracture energy of alkali-silica gel is an order of magnitude smaller than that of the concrete and 2 times smaller than that of mortar generally. More measurements are needed on a larger amount of fragments. We have illustrated a powerful method to measure the fracture properties of alkali-silica gel crystal from the nanometer up to the micrometer length scale. In conclusion, we use the scratch test to characterize the fracture behavior of alkali-silica reaction gel. To validate our method, we used indentation testing, and our indentation results of elastic modulus agree with other measurements. For fracture toughness, scratch testing has been applied to many other applications. For ASR gel crystals, we got 0.59, and for air-embedded specimen, and 0.62 for micro-embedded specimen. By combining the indentation with scratch testing results, we estimated a fracture energy of 11.17 and 11.95. The fracture energy of alkali-silica gel is an order of magnitude smaller than that of concrete and 2 times smaller than that of mortar. I will end my presentation with our scanning electron microscope of ASR gel crystal fracture surface on the top. And thank you very much for your time and listening. Thank you very much again. I will stop sharing.
Thank you, Jiaxin, for an excellent presentation of your work. Thank you for explaining to us how the scratch testing, the nano indentation works. We have a lot of time for questions, so please proceed, unmute your microphone and ask a question.
Shay, may I ask a question?
Yes,
thank you very much. Very interesting talk. So my question has to do with perhaps some details of the indentation test, and you stress the importance of the shape of the indenter. So is there any direction of research in which the shape of the indenter itself is optimized, modified, or engineered to replicate specific circumstances? And I'm asking this with a direct interest that has to do with the contact mechanics between particles, let's say sand particles with very complex shapes, in which the indenter itself is represented by a particle of an arbitrary shape which could be very angular, non-symmetric. And so what insight would you have in terms of playing with that aspect of the picture of the nano-indentation? And most important, with relevance to the threshold between contact phenomena in which fracture is predominant as opposed to those in which plasticity becomes predominant.
Thank you very much, Professor, for this wonderful question. So for the indentation indenter probe function, which is really important, definitely, and also Oliver and Fa, especially Professor Fa, has done a lot of research and work on this probe shape. And for our shape, we used like the Berkovich shape, which is when we have the indent, we have a triangular shape. But we definitely have like the spheral shape and also many other shapes. And usually for the Berkovich indenter is more commonly used in indentation to get the indentation modulus and hardness. But for other shapes, if I remember right, for different shapes, they have different applications. So for example, for some of shapes which is suitable for indentation to get the fracture properties, I definitely know like indentation can get the fracture properties of the specimen, but maybe not for the Berkovich shape. And also I know like yeah, this is definitely a great topic, and Professor Farr, which is the expert in indentation, have done a lot of work on that. I'm not the expert on that. I also know molecular dynamics can also do indentation as well.
Thank you.
Giuseppe, maybe I can ask a follow-up on that. And I'm curious, if we just take modulus measurement as an example, local modulus measurements, if you have a punch, right, which is more of a square-shaped tip, okay, and then you have a diamond tip, which I guess you call the Berkovich tip, right, which the punch surface looks like triangles, or if you have a spherical, tip. The question is which one of the three tips and why will give you a more accurate estimate of the modulus if you have, for example, a half space, and why?
So previously when we designed the experiment, by reading some like literature, they said like the Berkovich tip is a diamond tip is better for investigate the mechanical properties of the materials. And for the spheral shape, they said like when we have a spheral shape and when the spheral shape goes to the materials, there are usually some chips around the indenter. So therefore, maybe this is not accurate. And also when it's go to the tape, it takes some time to get the penetration depth if we use the spheral indenter. So that is my understanding, and that's why we use a Berkovich tape, because it has a spheral, but it has also a cone there. And basically the spheral shape is really small, and then if our penetration depth is bigger, we will definitely go to the cone zone. And then when we see the curve of the penetration depth and the force, we have a better curve of the raw data, and then it's better for us to get the dP over dA, and then get the elastic modulus and indentation hardness. I'm not sure if I answered your question.
Yeah, thank you, Jiaxin. I guess I can. If there are any other questions from other members of the group.
Yeah, I had a question, Shay, if now's a good time.
Yes, please.
Thanks, Jiaxin. Great talk. I'm interested in slides 19. Now that you're not sharing your slides anymore, and I know this is not your work. This is related to, as some of these other questions are too. It's related to work that came before you. But this really struck me. This image. I was curious to know why this pattern emerges. It looks like it's a pretty continuous scratch process. And then at some point, it starts to become a discrete process with some increasing amplitude in terms of the size of these and maybe in decreasing frequency. But, these scratch tests are kind of curious tests, interesting tests, rich tests, because they both you potentially have periodicity arising from the fractures that are forming, propagating, and then deactivating, and you form new fractures. But also you've got a contact problem to deal with, and you have the potential there for some stick-slip phenomenon. And it's entirely possible that those two are very intimately coupled. And all of this came rushing to mind as I was looking at this image. Can you give us some insight as to what is going on in this particular image? Is it one of these or none of this?
So definitely it's I think it's echo. Okay. And so for this image, the reason why is from the small deformation and then goes to a large deformation because we use a linear increasing force. That's why the magnitude of the crack is become bigger and bigger. So from the small and then goes to big. And then let's go back to the question. So it seems like the scratch testing is a combination of surface reaction and also like a fracture mechanics and also like a surface problem. It's not just like the fracture mechanics. It involves a lot of things. So when we design the model of our theoretical model, we neglecting the surface effects. If I didn't do it wrong. So we neglecting the surface effects of that, and then mainly we see the fracture-driven performance of these materials, and then we get our fracture toughness. I'm not sure if I answered your question.
Yeah, you did. Thanks. And I think the first part particularly is we can be confident that what we're looking at in this image, what we're seeing is the fracture surface. So this is directly related to fracturing, what we're seeing here. And then I guess this relates back to Giuseppe's question or what he was talking about. It's interesting to see that as a function of penetration depth, you have different ductile behavior at first, moving to brittle failure at the end. So thank you. That's enough for me. Thanks for the talk and answering the question.
Thank you. That's excellent.
Yes, Sinan, do you want to ask a question?
Yeah, can I ask a quick question?
Please.
So very interesting talk, Jiaxin. Coming more from the polymers or soft materials side, I was wondering if the method has intrinsic limitations as you go to lower and lower fracture energy materials, or conversely really high fracture energy tough gels and polymeric gels with complicated networks that have very high reportedly fracture energy. So are there specific properties such as hardness values, modulus values, or fracture energies around which this method becomes basically has a large error, essentially?
Thank you, Professor Kenseth, for the great question. So when I have also think of this problem before. So for indentation, we can definitely apply it to a viscous material like gel materials. I think Professor Kono is also working on this. But for scratch testing, it may actually we have to make a lot of assumptions for that, and because recently we applied on the brittle materials like the cement and also polymers. Well, even though the gel costs like the soft material, but we here use the gel crystals instead of the gel itself. And also because when we apply scratch testing, but I'm not sure if I'm correct, when we apply scratch testing on like the soft materials, I think the surface friction domains the behavior instead of the fracture domains the behavior. So if we want to apply it on the softer material, we may need a lot of efforts to figure out how to set up the experiment. That is my understanding.
Yeah, that makes sense to me. Thank you very much for your answer.
We still have a few minutes for questions. Hopefully we can get a question from a student in the audience.
Professor Balogun,
Oh, yes, please proceed.
Thank you, Jiaxin, for homeschooling me during these days. Yeah, so from my understanding from the talk, like the fracture energy is from the surface that you created when you scratch away the materials, right? And also from the SEM image, like there's some subsurface crack. Like in the calculation, do you have to consider the crack length or the length of those subsurface crack that you created? Because that must dissipate part of the energy, right?
Yeah, that's definitely a great question. But like, for my understanding, maybe not correct as well. When we calculate our fracture toughness, we didn't think about the energy dissipated from the small cracks. We only consider the big cracks, like the curved crack surface, as shown here. So when we have D over R is really large, and then we consider FT over square root of 2PA goes to horizontal and converges to a value, and then we obtain that value. So that's how we calculate our fracture toughness, obtain that value as our fracture toughness. And then, as you said, we definitely have like some small cracks developed here, but I think for the model, we haven't considered or based the calculation, the main point is the curved fracture surfaces, but we can definitely later on add that energy and see what will happen. That's a good point.
Okay, right now it's 12:27. We have time for a few more questions. Okay, I can take a shot at it. If you go to slide 29, I was curious about the dependence of your indentation modulus, right, on the fact that you're in air or in vacuum. If we think about the modulus of the material as being intimately connected, to the interatomic bond stiffness, I'm not sure exactly why you see a difference between the moduli of the two materials.
Yeah, so that is another question when we did the experiment. So we have the same question. So like, even though we embedded in the air and embedded in the epoxy, they should have a similar value. I think another point is because we use different load for different specimens. So I think that's we can definitely design a better experiment, but time has passed. So for the first one, the air embedded, we use a higher load of 100 millinewton, and for the one with epoxy vacuum embedded, we have 2 millinewton. So we think, okay, this we may think one assumption is like this is a microscopic indentation, and this is a macroscopic indentation, this is a microscopic indentation. So that's why we have a small difference in the value. But I would think I don't have a really good answer for that. But when we calculate the elastic modulus and also the fracture energy, we see they actually agree with each other, as you see, like 11.17 and 11.95. And yeah, we definitely have a difference in terms of the indentation modulus for different types of preparation. But it would be good if we apply the same load on the same on the two different specimens and see the values.
Excellent. So thank you very much for that response. We are right at 12. We're right at 12:30. I want to thank you all for attending Jiaxin's talk and also the questions from the audience. We look forward to the next talk, and I hope you do enjoy a beautiful day out there. It's sunny, maybe warm. I haven't been out there yet.
Cold but sunny.
Oh, cold and sunny. Okay, good.
It's virtually nice.
It's virtually nice. All right, so have a wonderful rest of your day.
Bye.